Welcome to Quick Course Digest. Today we're taking a deep dive into the incredible world of an introduction to chemistry. We're going to go on a grand tour of the fundamental rules that govern, well, everything, from the tiniest atom to the entire planet we live on. This is really the science of transformation, and we're about to break it all down.
So here's our roadmap for this journey. We'll kick things off with the basic language of chemistry, then we'll follow the flow of energy that powers our world. After that, we'll get into the tangy and sometimes bitter world of acids and bases, and then explore carbon, literally the backbone of life. And finally, we'll see how it all comes together in our own bodies and on our planet.
All right, first step, we need to learn how to speak chemistry. And like any language, it has its own grammar and vocabulary, but instead of just describing ideas, this language describes reality itself. And probably the most powerful sentence you can write in chemistry is the chemical reaction.
At its very core, a chemical reaction is all about change. It's the process chemists use to describe, well, pretty much any transformation, whether it's a nail rusting outside or your body digesting the food you just ate. You start with one set of things, we call those the reactants, and you end up with something totally new, the products.
Now, to write these chemical sentences correctly, we have to follow a fundamental law of the universe, the law of conservation of matter. Basically, you can't just create or destroy atoms in a reaction, you can only rearrange them. That's why we have to balance equations. It's kind of like a puzzle or a little accounting trick, using those numbers out front, the coefficients, to make sure the number of atoms for each element is exactly the same on both sides of the arrow.
But sometimes the full equation tells us a little more than we need to know. See, when reactions happen in water, some ions just float around and don't actually do anything. We call them spectator ions. Think of them like guests at a party who just stand in the corner and don't dance or talk to anyone. The complete ionic equation shows everyone at the party. But the net ionic equation, now that's the real story. It clears out all the spectators and only shows you the ions that are actually involved in the action.
But just shuffling atoms around is only half the story. Every single time those atoms get rearranged in a reaction, something else is happening right alongside it. Energy is on the move. Every chemical reaction either releases energy or it absorbs energy, and this flow is literally what powers our world.
So, energy really comes in two main flavors. You got potential energy, that's the stored up energy, the promise of action. A battery just sitting on a shelf, that is pure potential energy, just locked away in its chemical bonds. And then you have kinetic energy, which is the energy of motion. When water rushes over a dam and spins a turbine, that's kinetic energy in action. And chemistry so often is the bridge that connects the two.
Here's a number I bet you've seen 1,000 times, 1.5 volts. It's the potential energy that's stored in a regular old AA battery. This tiny, controlled chemical reaction is what's powering your TV remote. It's a very familiar, everyday bit of chemical energy. Okay, now let's look at the other end of the spectrum. This is the energy released by nuclear fusion inside our sun. It's a number so huge it's almost impossible to wrap your head around. See, the key difference is that a battery just rearranges electrons, but the sun is rearranging the very nucleus of atoms. And this incredible range from a tiny spark to a star's furnace is all governed by the same principles of chemistry and physics.
So, how do we actually harness all this energy? Well, this table shows a few of the big ways. We burn fossil fuels through combustion to get heat. We use controlled chemical reactions in batteries to get electricity. We can concentrate sunlight to boil water and make steam, or we can split atoms and release immense power. Each one of these is just a different method for unlocking the potential energy that's stored in matter.
Okay, let's shift gears a little bit. We're going to talk about one of the most important classes of chemicals out there, acids and bases, and they are absolutely everywhere, from the sour citric acid in lemons to the bitter taste of caffeine, and even the lye that's used to make soap.
We measure just how acidic or basic something is using the pH scale. And as you can see here, it's a huge range. But what's really crucial to get is that the pH scale is logarithmic. What does that mean? It means a change from pH 7 to pH 6 doesn't mean it's just a little bit more acidic. It means it's 10 times more acidic. So these small number changes actually represent huge leaps in chemical reactivity. And this brings up a really critical question. I mean, our own blood has a very, very specific pH it has to maintain, right around 7.4. If it shifts even a tiny bit, it can be fatal. So with all the acidic and basic things we eat and drink, how in the world does our body pull off this incredible balancing act?
Well, the answer is one of the most elegant systems in all of biochemistry: buffers.
Think of a buffer as a chemical shock absorber. In our blood, we have this carbonic acid bicarbonate system that's constantly working, grabbing any excess acid or base and neutralizing it on the spot. It keeps our pH locked in that narrow, life-sustaining range. It's this silent chemical process happening inside you right now that's keeping you alive.
This incredible internal balancing act really highlights a core principle in all of chemistry. Context is everything. It's perfectly captured by that old saying, the dose makes the poison. Water is essential for life, right? But drink way too much, and it can be toxic. And then there are substances like hydrofluoric acid, which are just deceptively dangerous. It's a weak acid, so it won't cause a bad burn right away. But once it soaks into your body, it silently starts pulling essential minerals like calcium right out of your tissues, and that leads to catastrophic organ failure.
All right, now let's turn to the undisputed king of the elements when it comes to life, carbon. The whole field of organic chemistry is just the study of carbon compounds, and it's the foundation for every single living thing on this planet. Carbon's incredible versatility lets it form the ridiculously complex molecules that make us who we are. The secret to carbon's power lies in something called functional groups. Think of them like little accessories you can attach to a carbon chain to give it a totally new identity and a new job. Let's do a quick fire round. First up, the hydroxyl group. You slap this onto a carbon framework and boom, you've just made an alcohol. A family of molecules you'll find in everything from rubbing alcohol to your favorite weekend cocktail.
Next, we've got the carbonyl group. That's a carbon double bonded to an oxygen. This thing is a true superstar in organic chemistry. It's the key part of aldehydes and ketones, which are the molecules that give us the smell of cinnamon and the flavor of butter. It's also at the very heart of the sugars that fuel our bodies and the hormones that regulate them.
Now, what happens when you link a bunch of these small carbon-based molecules? We call them monomers together. You get a polymer. It's just like taking individual paper clips and linking them together to form a long, strong chain. These gigantic molecules, or macromolecules, are the building blocks for so much of our modern world.
I guarantee you are surrounded by polymers right now. The plastic in your water bottle, that's polyethylene. The non-stick coating on your frying pan, that's a polymer. Even the incredible strength of Kevlar in body armor comes from how its polymer chains are designed. They are truly the invisible architecture of our modern lives. Okay, for our final section, let's bring it all home. We've looked at reactions, we've looked at energy, and we've looked at carbon. Now let's see how all of these principles combine to create the chemistry of our planet and the chemistry of life itself.
Let's start with the very air we're breathing. As you can see, it's mostly nitrogen, about 78% of it. The oxygen that we actually need to survive makes up just under 21%. This very specific chemical mix isn't an accident. It's the result of billions of years of geological and biological activity that created the precise environment that life needs to thrive.
So what is all this life made of? Well, it all comes down to four major classes of what we call biomolecules. You've got carbohydrates for quick energy, lipids to form cell membranes, proteins that act as little molecular machines and enzymes, and of course, nucleic acids like DNA and RNA, which hold the genetic blueprint for it all. These are all just large, incredibly complex organic molecules, all following the same rules of chemistry we've been talking about.
And that brings us to the end of our grand tour. We've seen how just a few simple rules about atoms and energy can build up to create the staggering complexity of our world, from a simple battery all the way to our own DNA. Chemistry is the science that built our modern age, so the only real question left is, what challenges will it help us solve next?